Hello everyone, this paper is about how dynamic memory allocation algorithms perform in a real-time system. The article is written by Isabel Puat. The purpose is to analyze the results of several different dynamic algorithms with real-time system in order to give a guideline to system developers. With the results, people can easily to choose a better allocator. So as to understand this paper's idea, some basic background knowledge need to be introduced. Memory management is a form of resource management applied to computer memory. At the beginning time of computer's history, CPU access physical memory directly. If there is a process who is running, it will occupy the whole physical memory. This is very slow and is a waste of memory in most time. Then people develop virtual memory to solve this problem. Virtual memory maps the access address to physical memory. This method involves different algorithms to allocate and deallocate memory. This attribution process called memory management. When the allocation of memory performs at the compile time, then it is known as static memory. When the memory allocation is done at the execution or runtime, it is called dynamic memory allocation. Besides memory management, the type of system is also crucial. Time-sharing system allows several users to use a computer system from various locations. Real-time operating system completes a task within a specific time. In this paper, authors mainly talked algorithm performance in real-time system. From the name of real-time system, we can guess that it has a strict requirement of time. Actually, it also has two types: hard real-time system and soft real-time system. Hard real-time system, which also known as an immediate real-time system, is hardware or software that must operate within the confines of a stringent deadline. The application may be considered to have failed if it does not complete its function within the time span. It is usually used in railway signal system, air traffic control system, nuclear reactor control system, and so on. A soft real-time system is a system whose operation is degraded if the results are not produced according to the specified timing requirement. In a soft real-time system, the meeting of deadline is not compulsory for every task, but the process should get processed and give the result. Usually used in DVD player, video game, web review, mobile communication, and so on. So the developers of real-time systems avoid the use of dynamic memory management because they are afraid of that the worst-case execution time of dynamic memory allocation routine is not bounded. or is bounded with a large bound. In other words, people don't use dynamic memory management because the running time will be very bad. According to the definition of real-time system, it can't be accepted. So the author did these experiments want to give out a guideline to solve the dilemma. As illustrated in last page, real-time system contain hard real-time system and soft real-time system. In hard real-time system, the knowledge of tasks' worst-case execution times is an essential input parameter of the scalability analysis used to validate the system temporal correctness. Soft estimations of worst-case execution times of programs can be obtained using static analysis of their code. The author gives detailed average and worst-case measurements of the timing performance in a comprehensive panel of dynamic memory allocators. In the paper, 4 different allocators are used in experiments. The author compare worst case and average time behavior for each allocator. The data come from actually executing real and synthetic workloads. The main contribution of these experiments contain 2 parts. The first one provide an analytical and quantitative evaluation of the worst case allocation and deallocation times for given hardware platform. The second one provide a quantification of the impact that could have the consideration of worst case allocation times obtained analytically on the application's end-to-end execution time. As mentioned in previous page, the author did experiments in order to provide guidelines of how to choose dynamic allocators in real-time system to developers. The reason is that the worst case execution time of dynamic memory allocation routine is not bounded or is bounded with a very large bound. The author also provides the information of the experiment's workload. Some are real workloads and the other are synthetic workloads. The purpose is to implement algorithm in real and in extreme situations. In the experiments, author used 4 kinds of dynamic algorithms. They are sequential fits, indexed fits, segregated fits, and body systems. Sequential fits are based on the use of a unique linear list of all free blocks in memory. The authors use a doubly linked list to chain the free blocks in the first fit and best fit allocators. Indexed fits are improved a bit by using data structure to link the free blocks. They use binary tree in first fit and Kelson tree in best fit. The segregated fits are called quick fits in the experiments. It actually uses 2 different allocation algorithms depending on the size of requested block. Same as segregated fits, They also use two allocators, which are binary and Fibonacci body allocators, depending on the type of block size in the class of body system. These algorithms have some common features. Allocation in real memory. Since authors focus on the real-time system, they have restricted their study to algorithms that allocate areas of real memory and assume that no address translation nor paging is used, and there is no block relocation for memory defragmentation. Immediate coalescing. A block is merged with its neighboring free blocks as soon as it is freed. Minimum block size. The size of a small allocated block is rounded up to a minimum block size. Splitting threshold. Upon allocation of a block, when a free block larger than the request size exists, it is split only if the remainder is larger than a known constant, named splitting threshold. To obtain quantitative data of the worst-case execution times of memory allocation and deallocation, the authors have measured the execution times of the allocation and deallocation on workloads that are representative of the worst-case scenarios. The author chose three workloads, which are MPG123, CFR, AC, and ESPR. But one is a soft real-time application. The other two are not real-time applications. However, the author gave a reasonable explanation that there are few dynamic memory management in real-time systems. About the synthetic workloads, the author generates random values by three characters, which are the mean block size, block lifetime, and the mean time between successive allocation requests. Measurements were conducted on a Pentium 90 MHz machine. An initially empty 4 million bits heap is used in the experiments. The smallest value for minimum block size and splitting threshold possible for all allocators is used in the experiment. The author compared worst case and average running time with different algorithms and gave out the results by charts. In the paper, the running time is recorded in the style of CPU circle. It contains two main parts, allocation and deallocation performance. The result is the identification of discrepancy between the allocators with the best average performance and the allocators with the best worst-case performance. At last, the author discussed the impact of heap size. As we know, in the experiment, the heap size is 4 MB. The author gave some inference of the effect with different heap size. This paper has given detailed average and worst case timing analysis of a comprehensive panel dynamic memory allocators. The result of the performance analysis is the identification of a discrepancy between the educators with the best average performance and the educators with the best worst case performance.